Hello students, welcome to the NPTEL video course on digital verification and test of digital VLSI circuits. As you know, the course has 3 modules, so design, verification and test. As of now, we have already discussed in detail the design phase and the verification phase of VLSI circuits. So now we are going to the third module, that is on the test of VLSI circuits. So as we have already discussed in the first module, that we start with, when we go for digital VLSI design, we start with what you call is the specification of a circuit or specification of a design. Like for example, we have seen very detailed or descriptive specifications like how to design a control flow or how to design a adder, or as simple as how to design an adder, or as complex as how to design a control flow of a complex mechanical system, etc. And then we have seen that we write this stuff in some kind of a very simple user language or which is not a technical language. Then we have seen that it can be coded in form of something called Verilog or VHDL, some language we write down the specifications, and then what we have to do is that we have to go for a architectural synthesis, that is scheduling, allocation and binding. That is, in case we say that for a given specification to be realized, how we can optimally schedule the operators required in the given time steps, and then we have seen that how individual operators, or that is the hardware operators, are binded and allocated to this operation. So this was the high level synthesis part, which we have already discussed in details in phase 1 of the course, which is on design. Following that, we have seen that given a RTL design, that is register transfer level design, we go for a RTL synthesis and and logic synthesis, that is the RTL design and logic synthesis. In this case, finally we get here is a gate level, Boolean gate level design of the circuit. So this first part, as we have already told, is called the design part or the front end part of VLSI design. Following that, we go for floor plan placement and routing, that is the back end part of the design, which we have not discussed in this course. But this first phase of the design, this is called the VLSI design part, which is actually the module 1 of the course, has already been discussed. And after that, in module 2, which was the verification part of the course, we have seen that from one phase to another phase, like from specification to architecture design, from architecture design to RTL, and then from RTL when you go for logic synthesis, that is we get the gate level design. So for the same specification, we get different form of representation. Like in this case, we can get a control and data flow graph kind of a stuff. For where we get the logic, after the logic synthesis step, what do we get? We get is the Boolean gate level circuit. In this case, what we get some kind of, what do you see is that operators in some logical, what you call the time steps we have seen. So same specification like addition, control or something, we have different representation. So every step has to be verified that it is equivalent to the previous specification. That is, finally when we have our circuit realized, it should be equivalent to the specification we have been given. So every step should be equivalent to the previous step. So this part was called the verification step of VLSI design. So this part has also been discussed in detail in module 2 of our course. After that, we have also discussed in brief in very few initial lectures that after the circuit has been designed, so it has to be tested. That is, the hardware, after the fabrication, we get the hardware of the circuit, that is the chip or what you call the package chip or the wafer. Now we have to verify that whatever you are shipping to the customer is electrically correct. That is, whatever input signals you give and the outputs you obtain should be as per what you called is the specification that we have required. So that is actually called the manufacturing test. That is, once the circuit has been designed and fabricated, it should electrically meet these specifications. So then what is the test? That is actually the manufacturing test. But as you know that VLSI circuits are very complex, and a circuit with having say input of n input, if a circuit has around n inputs and around say m outputs, then to find out that whether the circuit is matching electrically all the parameters of the specification or all the specification we have mentioned in our requirements, then we require order of 2 to the power n input vectors or 2 to the power n input combinations has to be checked. But as you know, if n is 1000, then 2 to the power 1000 is an prohibitive number to be tested. So, we have to go for an optimal test, or what you can call, our test should be such that we apply much less number of vectors than 2 to the power n, or a very less number of input cases you can apply, and then you have to say confidently that the circuit is working perfectly up to a extent, and the extent should be around say 99.9% accurate. You have to tell that the circuit is operating fine and with the much less number of test vectors than 2 to the power n. So, that for that we require a very detailed test planning, that how you can achieve this. So, this part is actually called the test planning. So, in this course, in the third phase of the course, that is on VLSI testing, we will be mainly discussing how test plans are made and how you can get a very good coverage, that is you can get about 99.9% plus accuracy with a minimal number of test cases you can apply. So, this is basically what we are going to study in this module. So, let us go ahead. So, what is the philosophy of testing? So, it is a very well known Murphy's law. It says that if anything can go wrong, it will. That means, if there is a probability that a system can fail, definitely it will fail. There is a very high chance of fail, and our life as test engineers, we should be able to find out that which is the chip or which is the system that is not working properly, that has to be discarded, and whichever is working properly, that can be shipped to the customer. So, testing, if you take a very simple dictionary meaning, then it says that testing a system comprises subjecting the system to inputs and checking that the outputs and check the outputs and verify that the outputs are as per the specification targeted using the design. So, in other words, what do you mean by testing? So, you have the system, then you apply some inputs and you get some outputs, these are the inputs, and you get some outputs. Now, this output should be as per the design specification which you have told, and so this is actually the output response which is to be matched. Now, the question comes, what inputs I will give? So, if you are given enough time and you have infinite amount of time available for testing, so you can apply as large number of inputs as possible, and your confidence on your testing will rise. But in a practical scenario, the number of inputs to be applied during testing will be much less because of the time constraints, and there are several other constraints which we will study in this course. So, our main goal is that you have to apply as low number of inputs as possible to meet the constraint, and your outputs should be matching the specification. So, what do you call, your output should match specification as large as say around more than 99% plus, or as close as possible, maybe 100%, you have to reach that. You should show that your outputs are matching the specifications to that extent. So, our goal is to take the outputs to a level that you can say confidently with a very high confidence that outputs are matching all the specification, and at the same time you have to apply as less number of inputs as possible. So, this is the testing philosophy. So, coming to the next thing. So, before we go for really a VLSI or circuit kind of testing, let us start with a very simple example of an electrical iron or a classical system. So, what do you mean by testing an electrical iron? If I ask it to a layman, so he or she can say that you just plug in your iron to a 220 volts AC and see if that heating is there. So, for him this is a testing, and in fact even in technical terms this is also a proper kind of test, because our input specification for a heater is for an electrical iron is that you plug it, it will be heating, and then you can go on for ironing. So, this is also a proper kind of testing. So, and the technical name of this test is called this is actually the functional specification, and so we are actually testing it functionally. Now, let us see what more or how integrated testing is, you can also understand from this example. So, this is a functional test and this is also partial. But now, as you know that electrical appliances like electrical iron, there is a lot of safety features that should be presented. That is, all the exposed parts of the iron should be grounded, so that there is no short circuit. Secondly, there are many others, I am just listing 2 or 3. So, for example, if I just put the iron on and then I forget it for some reason, then after a certain amount of temperature, it should go on for auto off mode. So, there are some other specifications that are coming into picture that are not that much related to functionality, that are related to safety part of the specifications of the electrical iron. So, you can see that slowly the number of testing or number of tests that required to verify that your system is operating properly is increasing. So, this is another part of the safety. So, you have to find out that whether everything is grounded, and you have to subject your iron to some overheating, and then find out whether that it is getting automatically switched off or not. Following that, if I go to a bit sophisticated electrical iron which we can always see, which you are nowadays which are available, then you can see that it has a lead. So, when you put the electrical iron on, so when the heating is going on, so a lead glows, and whenever some threshold temperature is reached, this thermostat detects the threshold has been reached. So, it switches off the heating of the electrical iron for some time, and then there is the LED becomes off, and it goes on in this round. So, along with that also you have to test, if I am going for a detailed functionality test. So, I have to also see that the LED is properly working or not, that whenever the heater is on, it is heating, then the LED should be powered on. Whenever the specification it is reaching that some for example around say some degree centigrade reached, the heating is off, then the LED should be LED should be off, and so forth. So, this is another part of the testing. So, for example, electrical iron has sometimes have a thermostat, as you might have seen, and there is something called silk, I think you might have seen, then there is called cotton. So, for all these things you can have different temperatures, and if you have different temperatures, then the thermostat works accordingly. That is, so if you have set for the say cotton kind of a cloth, then if the temperature is say around 80 degrees centigrade or something like that, then it goes above, then it switches off, and when it is for silk, the threshold will be different. So, you have to if you have to go for that elaborate kind of testing, so you have to set the regulator to woolen, silk, cotton, etc., and then again I have to see whether all these functionalities like auto cut off, then LED glowing, etc., has to be again tested. So, in other words, what I am saying is that even for a very simple system like electrical iron, it seems that testing can be as simple as plugging it on and see whether it is working, whether it is heating or not, but in fact this is not the case, because whenever you go for a detailed kind of functional test, so you can see how elaborate testing becomes. So, now let us see, so the previous slide we discussed only about the functionalities of the circuit, like different thermostat settings like cotton, and whether a LED is glowing, whether it is heating, etc. But there are some other performance which is done, which is not that much relevant directly to an user, that is actually the performance. We say that the heater, you say that nowadays the electrical iron is 5-star compliant. So, it says that the power consumption of the heater or the electrical iron is such and such. So, you have to also see the power consumption. So, that has also to be reached. Then also for some branded companies we say that the temperature that will be reached by the iron will for cotton setting or for some silk setting, it will be reached within X seconds or 10 seconds or something like that. That is the performance, that my electrical iron is so good that it consumes so much power, so less power, and it reaches a desired temperature in such a low amount of time. So, these performance testings are also very important. So, I mean the more testing you require, the more time it will require, and the test procedure will become more and more complex, even for a very simple system of like a classical iron. But these were some of the tests which were related to the electrical properties of a iron. So, you can see that the whole Pandora's box is slowly opening up. So, now you can see that there can be some mechanical parameters, like you can say that the plastic parts of the electrical iron are unbreakable, that is, or it is resistant to breaking. So, but on from how much distance if I throw it, or from how much distance this force falls on a wooden floor or it falls on a tile floor, what will be the breaking, whether there will be scratches and all. So, there are some kind of other tests which you may also require to test mechanical parameters or something like that. So, tests become so complex that you have to have more time for this. Now the question is, more I do a testing, better is my product and better I can advertise it. So, why should I do a less amount of testing? Philosophically testing, or for a common person we can say that we should test as much as possible. That is true. If you go for a exhaustive kind of testing like for electrical iron as I have discussed, so what you can get? You can get a very good test result and you can say exactly about your iron specification when you are selling. But now what happens? Now say for example you are manufacturing 10,000 electrical iron per day. So testing all the parameters as I have discussed may take even more than an hour or even more than that to say that my each electrical iron satisfies all these properties. So now for each heater you are spending around 1 hour for testing. So, you have to devote man hour, you have to devote electricity in your test plan, and you have to also devote so many other things. So, you are adding into cost. So, now actually decided by that, so everything is decided by the target price of the product and some efficiency which will come later. So, you can say that if I want to sell my electrical iron at 5,000 rupees something like that, then you can go for the huge amount of test. But as you know, in a practical market these things would not survive, because even a very good electrical iron nowadays come below 1,000. So, now you have to decide that I have to make profit in that 1000 or some x amount of money, and at the same time I have to give a reasonably good amount of testing I have to do, so that I can also satisfy the customer. So, there is always a trade off between the number of tests performed. If you do a large number of tests, then you can always go to a very ideal result, say that my heater or my whatever performs this, but at the same time it will increase the price of your design of your product. So, there is always a trade off in between this. So, with this we started with a very simple classical example of an electrical NAND, because very well known to us. Now, slowly we will go to our original course, which is on circuit. So, we will start off with a very simple NAND gate. So, this is your very simple NAND gate. So, now again I need to test the NAND gate. So, what is the very first, if I give to a person that you have to test a NAND gate, so what he has to do? Similarly, like an electrical iron, so you just test the functionality. So, what was the test in electrical iron? Just plug it and test it. So, in this case also I go and go for a functional test. So, you can see that I have 2 inputs and 1 output in this case. So, there can be 4 inputs in this case, there is 0 0 0 1 1 0 and 1 1. So, these are the input cases. So, all the inputs I will give, and then I will see whether the output in the first 3 cases should be 1, and if the input is 1 1, the answer should be 0. So, if I find it, I know that the gate is okay. I can say that the gate is functionally okay. So, but now you must be surprised to see that this is just the very starting point of testing a NAND gate. So, now just like heater, just like our electrical iron, we will start opening what kind of tests are possible in the NAND gate. So, see, so first is the digital functionality. So, it can be done according to the table of 1 that we have already discussed, that is all the 4 patterns 0 0 0 1 1 0 1 1 you give and test it. Now, you see, now this is a say a NAND gate. So, now you have connected it to some kind of a circuit. Now, another very important part is the time. So, that is the delay. So, you might have always heard, or we have already discussed in the first 2 modules, that the circuit is working at x gigahertz, or this time, or the time required by an operator, like an adder or a multiplier or some hardware is x and x nanoseconds, or its frequency is so and so. So, all this speed will depend on the delay, that is, if some input arrives here and if some output arrives here. So, what is the time delay of this gate? So, if this gate is having a very high time delay, so obviously the whole circuit which will be composed of so many small gates will be also large. And if you want to go for a minimum delay, or you have to increase the frequency or the performance in terms of the speed of your circuit, so these gates should have a lower delay. So, that is, delay is a very important parameter in case of circuits. So, you know that functionality is fine. Now, if I want to ship my gate, or if I am to say that I have manufactured this NAND gate and I want to sell it, another very important parameter is the testing, that is actually called the delay test. Like in electrical iron, you can say that if I am a very cheap iron kind of a thing, so I can say that you just plug it into the electrical phase and it will start heating. That is the bare minimum test. But in case of a VLSI circuit like a NAND gate, digital functionality is one, and the very important functionality which you have to do is the delay test, because unless you say that what is the time required by this gate, nobody is going to accept the design, because when he is plugging your gate into your circuit, he should also know that what is the amount of time required by that gate to give the output. Accordingly, he can go for his design, because when he is shipping his product, his digital functionality as well as your performance in terms of speed is very important. Like you might have heard that in case of when you are selling your Pentium processors or AMD processors or whatever, you say that there are 2 things. It says that it is Pentium 3 or Pentium 4 or dual core. So, that tells that what is the basic functionality, and also it tells that it works at 2 gigahertz or it works at 1 gigahertz. So, what that specify? That specify that the frequency of the circuit is so much. So, they are very 2 important parameters which has to be tested. So, now how do you go for a delay test? So, the delay test will be like from 0 to 1. So, initially in the NAND gate, this was the gate say. So, initially the output was a 0. Now, you have to make the output 1 for because of some inputs, like maybe the input was in that case, say in this case it was input was 1 1, and now say input is 0 0 kind of a thing. So, the NAND gate output will rise. Now, the question is how much time it will take to rise. So, this is a very ideal scenarios. So, these gates are very ideal scenarios. So, now you can say that that if you have given an input this stuff and then it rises in this way, this 0 delay kind of a thing is a very ideal stuff. But generally we will have a some delay like this. Now, I want to find out what will be this delay, will it be 1 nanosecond, will it be 0.2 nanosecond and so forth. So, I have to do, now you can see how the complexity it will become. So, from 0 to 1 I have to test, that is the rising of the output of the NAND gate. So, initially if you have, I want to get a 0 over this, I have to apply a 1 1. So, V equal to 1, V1 equal to 1, V2 equal to 1. Now, you have to find out what is the time required to change the output from 1 to 0, sorry, from 0 to 1. So, what is in NAND gate, output can be 0 or if only if the V1 is equal to 1 and V2 equal to 1, but output can be 1 in case of NAND gate in 3 cases, V1 1, V2 0, V2 1, V1 0, V2 1 and both are 0. So, now what you have to do in this NAND gate exhaustively you have to keep 1 1 here and then it will be 0. Now, you apply a 0 1 over here and see how much time it requires for this one to go high. Next you take V1 1 1 and then you apply V1 equal to 0, V2 equal to 0 and see how much time it requires for the change. And similarly, in 1 1 and from 1 1 you change to 0 0 and then you see how much time is required to change. And average you can tell that in the average case this is the time required for the change from 0 to 1 in the NAND gate, and also you can say in the case of worst case maybe from example from this one to this one the change required is so much nanosecond. So, this is the delay test from 0 to 1. Now, again you can also have to have a delay test from 1 to 0. So, you know that in a NAND gate already discussed. So, we can have a out, this is this curve we are requiring, we require how much time it requires for this delay, because initially it was 1, now it is falling to 0, this delay is I required to find out. So, initially how do I get a 0 in the NAND gate? You know that the answer has to be 1 1. So, all 4s will be 1 1, but how, from where I can reach a 0? The answer is if the inputs are both 0 0, the answer is 1, this one and this one. So, from these 3 input cases, if I go to these output cases, I can get a from 1 to 0, this fall is there. Again you have to apply the 3 cases and you have to find out that what is the time delay that has been taken for this fall, and then you can again represent that the delay from 1 to 0 fall is so much in the worst case or in the average case is so much. So, so now we have how many tests till now we have done? We have done 4 for this basic functionality, and then what you can say that now we are doing this delay test. So, we are applying another 6 kind of a parameters which we have, or 6 kind of inputs, 10 inputs till now we have given. So, this was about the functionality of the NAND gate in terms of logic as well as the delay. Now, the another important thing which you all sometimes take into picture, that this is your NAND gate. I think you might also have seen the fan out case in our previous modules, that now this NAND gate can drive or needs to drive several other gates. Now, the question can be asked that how much gate or what is the drive capability of this fan out, or what is the fan out capability or the drive capability of this NAND gate. So, I am not going into details of how the test can be done, because that is the requires some complexity to perform this test, but again you have to tell that okay, these gates can pretty well drive so many other gates with so much load in so much time. So, this is about the fan out capability test. Now, again if you look at the digital design, as well many times I have told that we mainly go for 3 stuffs in design. So, one is speed, that is frequency, speed, power and delay. So, now so till now we have seen that this or what do you call we have seen the delay, and that is the function delay, that is rise to 1, fall to 0. So, this delay parameter we have tested and we can report it. Another very important constraint which we say is the power constraint, that is actually coming into prominence nowadays because of the fact that we are using lot of handheld devices like your mobile phones, your laptops, etc. So, many times we say that our laptop or your processor is working at so much frequency, its speed is so much, that is its frequency, and then at the same time we also say that its power, that what is the power of your circuit. Sorry, delay and speed are the same thing, actually I meant area. So, we will afterwards we will come to area, that is what is the area taken by your stuff. So, the 3 parameters of design are area, delay, that is same, speed and power. This is not, it was not speed and delay are the same thing, sorry for that. So, this is area, delay and power. So, delay we have already measured, then and we can perform the delay test. Now, also you might have heard that we sometimes say that our processor like an atom processor is a very low power processor or it consumes low power. So, also you have to find out what is the power required by your AND gate, that also you have to tell. So, if your AND gate is very fast, it is functionally very fine, but it takes a lot of amount of power. So, that may not be also good for your design. So, along with this delay test, also you have to go for a power consumption test. So, I am not going into details how the power consumption tests are done, as they may be pretty complex. So, we generally measure two types of power. One is the static power, that is when the gate is not functioning, still there can be some power loss because of leakage, and there is something called dynamic power, that when is your circuit is switching from 0 to 1 and 1 to 0. So, there will be also some kind of a power loss, that is dynamic power. So, you have to measure those power. Then you can say that the power of my circuit is this much, the delay of my circuit is so much, functionally it is correct. In area we can measure from the design part, that is when you have done your designed your circuit, then you have done a back end, that is you have done layout and fabrication has been done, you can also report your area. So, area we generally do not cover under testing, but you can directly report this is the area. So, minimum these 3 parameters we give, and these things you generally can verify from your test results and say that your NAND gate is such and such. Okay, so, these are your around, you can say that the logic boolean functionality kind of a thing. Now, that is depending on your functionality and all those. Now, another very important thing, we always say that, so slowly you can, I am telling you that to test a basic NAND gate, how much sophistication it is. So, that is how we also started with a very simple example of an iron, and then we saw that what are required to be tested in that iron to get very good amount of what you call test results or very good amount of confidence. Same thing we are doing for a electrical, for a VLSI circuit like a NAND gate, and then we will do the comparison to give you the philosophy. So, now what another testing that is required, we say that logic 0 and logic 1. Basically, there is nothing called logic 0 and logic 1. There is some voltage that corresponds to logic 0 and there is some voltage that corresponds to logic 1. Generally, we can say that if it is a say some kind of circuit where 5 volts is considered as the upper threshold and say 0 we consider as the 0 volt we consider as the lower threshold, then we can say that if anything is around above 4.8 volts and to say 5.2 volts or something, so we can call it the logic 1. And logic 0 we can say that if the voltage is up to say 0.3 volts or something, we say that a logic 0. So, this specification I say that if I get something less than 0.3 volts or below, I call it logic 0, and from 4.8 volts to 5.2 volts I consider logic 1. Now, again all the tests I have done for zeros and ones, I have to apply this all the inputs in case of NAND gate in the table 1, as we have already seen that we apply 0 0 0 1 1 0 and 1 1, and then we get the answer say 1 1 1, and then we get 1 1 1, and after this some pattern we get the answer 0. Now, for each you have to measure what is the voltage, like for all the ones your voltage level should be within 4.8 volts to 5.8 volts, and for 0 volt it should be within say 3.3 volts. So, now you have to measure all these things using analog techniques, because digitally we cannot measure volts kind of a stuff, and then you have to find out that this all the voltages at the logic 0 and logic 1 and everything is meeting. So, your logic 0 and logic 1 are compatible with the input voltage ranges. Now, again, now you know that your circuit can be subjected to another set of tests. So, it can be subjected to very extreme conditions, like it can be subjected to your, we say that your VLSI circuit or your device or whatever will work properly, say for example from say 5 degrees centigrade to around say 60 degrees centigrade kind of a thing, we generally write that. So, your device will work properly within so and so temperature. If it is a military grade equipment, we say that it operates from minus 60 degrees centigrade kind of a stuff, say it is just an example, may not be correct, but say from some minus x degrees centigrade to some plus x degrees centigrade. So, all the tests which I have done now have to be done for extreme low and high extremes, which is actually claimed in the specification document. So, if it is temperature, you have to do all the operations at such a high temperature, and also if there is some specification like it can work at so much pressure of the mercury and so forth. So, all the tests we have done have to be also verified at this high extreme test conditions we have to apply, and then only we can say that your NAND gate is actually operating at this, or it is satisfying all the conditions which is required in the specification document, as well as all the things, or your NAND gate will operate functionally correct and with all the parameters like test parameters like power consumption, threshold, delay, etc. within so and so degree of temperature and so degree of pressure. So, now you can understand the complexity that for a simple NAND gate with 2 inputs, what is the amount of test I have to do to assure that it works at so and so frequency, it operates at so much and so delay, it takes what do you call this amount of power, and this is the voltage levels, and it operates at this and this. So, all the things I have to do for a simple NAND gate. So, you can understand the complexity of testing a circuit to assure that it is operating properly. So, this till now we were talking about the NAND gate only from the logic level point of view, that it is a digital NAND gate, but actually if you look at the NAND gate from internal, so it is not a simple NAND gate, is not just like a digital stuff we understand. Inside it will look like this. It has 2 PMOS transistors, it has 2 NMOS transistors, it is connected in this way. Now, if you want to say that your NAND gate operates properly, sometimes we have to go for detailed tests of these transistors. Okay, and then only we can say that your transistor, all these 4 transistors operating properly. So, we can guarantee much better tests or much better specification coverage for the NAND gate. So, I will not go into very details of how the tests of these MOSFETs are done, because they are part of analog testing, but just to give you an idea. So, you can see you have to find out the output characteristics of all the transistors, like a set of input current versus input voltage current for different values of vote to drain sources. Then also there can be again some threshold voltage tests for those transistors. Also there is some substrate source voltages for constant VDS. So, they need not go into the details, but for each of the transistors like this, we are testing what is the voltage, what is the this current versus this voltage at constant, this one, and so forth. So, some of the parameters we are keeping constant, and we are studying the voltage versus the current for this type of thing, and all the transistors we are doing that, and then we are reporting the results. So, more depth we go, more amount of tests are coming into picture for a NAND gate. So, that was about the transistor level design, but now how a transistor is designed? The transistor is when you are laying out the transistor in a physical backend or in a VLSI circuit. So, your one single gate NAND gate generally looks like this. So, this is your metal, so this is your N diffusion, this is your poly. So, this is a physical layout of your circuit. Now, if I want to test this, things will become much more complex, and the device required are now you have to have an electron microscope kind of a thing, because now I say that for the NAND gate I say this specification is say 0.5 micron. So, if this is much more than that, then I can say that it is not as per my specification. We can also say that the distance between say these 2 metals should be say 0.7 micron or some specification. Now, after this has been laid out, now you can go for a very complex microscope, or there are several other very complex techniques to find out whether whatever was your minimum requirement for this kind of a NAND gate, it has been properly laid out, because laying out a circuit or fabricating a circuit is also a very complex procedure. So, we do not know that after the fabrication, because all the faults in your circuit, as we will be slowly looking in this series of lectures on testing, mainly happens because there are some what you can call that is some problems in this fabrication. That is the main thing. So, if I tell you what is the difference between verification and test. So, verification and test. So, in verification what do you verify? You verify that I wanted to design an adder. So, whether if I have really written a code that actually has the adder. So, that is what I verify, that it is functionally what I intended to design, what I have designed or not. So, if there is any failure in the verification phase, then you can be sure that it has happened because it was the designer's mistake. But when we say that testing, so what does testing verify? The testing verify that I had my design say D1, I have verified it. So, if I verified it, that means all my mistakes have been taken care of, and now I am getting a design D2 say, which is functionally correct. That means whatever code I have written, that actually implements this specification. Now, this D2 will be manufactured, and so manufacture, you say a chip I get is manufacturing say M1. So, what is the manufactured chip look like? For the NAND gate, it will be basically looking like this in a die. So, now this fabrication process or the manufacture process has lot of imperfections. So, we will slowly see why they are. So, because of these imperfections, this M1 may not be equivalent to your D2. So, testing procedure basically tests whether there has been any problem in the manufacturing step, that your M1 is not becoming equivalent to D2. So, that is why truly speaking, you have to find out whether this has been properly laid out, this has been properly laid out, whether this thickness is proper and not, and the test equipment and the test time are enormously and it will be exceptionally high if you are going for a test at this level. So, what we have seen is that basically this is the layout of a NAND gate, then we have seen the transistor level of a NAND gate, then you have seen that the electrical parameters of the NAND gate like delay, power, and then simply the functionality of a NAND gate like 0001, 1011 kind of test. So, more in depth you go, the more number of tests you have to do for a VLSI circuit as in the case of a classical system. And you can understand that a modern typical processor has millions of 2 input NAND gates. So, you can understand that what is the complexity of testing. So, what is the basic idea? Our idea of testing, as I already repeated, that for in case of the NAND gate or for whatever circuits, that your accuracy should be very high, more than 99%, and your test time should be very low. See, even less than a millisecond, because as I told, a circuit may have millions of gates, and if you start taking 1 or even 1 or 2 seconds for one chip, so one circuit will take 1 million seconds to do it, which may run into days, and we know that for a single design we fabricate millions of circuits and we sell in the market. So, your test procedure here will run into hundreds of years. So, that is not possible. So, what we have to do? We have to have as high as 99% accuracy, and we have to test should be less than a millisecond. So, all digital testing procedure or digital test planning is how can we achieve this magic. So, we will in this course we will see that. So, now if I say about digital testing is not say that, so if you say me ask me what is digital testing, so from a layman point of view or from a person who is not experienced in testing, he will say that digital testing is testing digital circuits. But to be more precise, it is not testing the digital circuit, because digital circuit testing we have seen such a complex case of NAND gate. So, you have to go for functional testing, speed testing, delay testing, power testing, threshold, and then for the layout. So, that is very complex. So, even if I start doing this, I will take even more than 1 hour to test a circuit, and for one gate, and a circuit will be in days, and for 1 million circuit will be in years. So, basically I do not have time for such a sophisticated thing. So, basically digital testing is defined testing a digital circuit to verify that it performs the specified logical functions and in proper time. That is, I am not much bothered whether it is taking whether the layout is proper or not, or whether it is there is some issues in the poly or some stuff. So, basic, this is actually we should solve the basic, because more if you become if you call it sophisticated digital testing or advanced digital testing, then it will become more complex. The very basic digital testing is that I want to know that my digital NAND gate is performing proper in case of 0001, 1011, and it has to give me the result in proper time. If this is done, more or less my basic digital testing is over. So, digital circuit is not about testing the digital circuit entirely, which you have seen in the last few slides, but it is basically this much, it is a basic testing. But if you want to go for advanced testing, so all these things will come into picture. Okay. So, now we have seen about two systems. One was the classical system of iron and one was the gate. Now, let us just have a very quick look at what is this, what is the basic difference or basic similarity in between this. So, in case of classical systems, we never go on for a very complex testing like electrical iron, which I have mentioned. We generally do a very preliminary test and then you are satisfied. Now, why? But for circuits we have to we have to exhaustively test all these circuits, or it is much more complex than a system. But why is it so? Because in case of electrical system, the technology is very well matured, that we all know how to design an electrical iron, and the technique is remaining similar for last say 30 to 40 years with slight modification. So, whatever we produce are more or less guaranteed to be working fine. So, a random testing kind of a thing with a few samples is fine. But in case of circuit, now we have a technology say 0.5 micron technology. So, we are having lot of problems with the technology, manufacturing is not proper, then we quickly go for we are having lot of issues, so some tests are failing, but still we are going for 0.5 micron technology. But due to market pressure, some other companies they come up with say 0.25 micron technology. So, even before 0.5 micron has matured and there is very little scope for errors, a new technology is coming into the market, because you are going to get better performance in the lower sub-micron, then people are quickly moving to new technologies. So, even before a technology matures and faults tend to decrease, that is technology has matured and it has stabilized, we go on for newer and newer technologies. So, always test faults are enormous in number and testing is a prominent thing that has to be done. But in case of classical systems, so this is the other way around. See, another important part I will go, this part I will come to later. This is we'll move to the course and then we will come in the end. So, another thing is yield. So, now in case of classical systems, we say that yield is almost 100%. That if I make 1000 electrical irons, you can know that say around 99 will be operating fine, or maybe all hundreds can be sold with little repairing. But in case of circuit, idea is not that, because the technology is always maturing. So, yield is even as low as 50%, that I make 100 chips, 50 I have to throw them off and only 50 will survive. Then that is why if such a high amount of failures are there, so you have to go on for testing each and every part, because if I miss, then there is a very high probability that I can ship you or the customer a faulty chip. But still how the VLSI people make profit? Because they can sell it in a slightly higher price, that is not the issue, but I always have to be as per the markets. That is, if I have a very nice Nokia mobile phone or a very nice Motorola phone, I will go for that rather than a very old kind of a phone, because always the technology is maturing in case of VLSI and we are getting newer and newer gadgets. So I can slightly go pay a higher price if I get a very good gadget. That is what is the, or a very good performance. So that is why we all are going towards newer and newer technology, even if there are errors or even if there are faults, so that 50% of my circuits I am ready to throw out, but still I have to catch up with the market with the latest trends. So with the high number of faults, so that is why testing is so important. Secondly, in case of classical system, tests are very simple, just you plug it on, or even a simple technician can do your test. But in case of this electrical, but the VLSI circuit, as you have seen for the NAND gate, it is a very tough process. You can see that you require microscope, sometimes you require to measure voltages, sometimes you have to add patterns. So very expensive equipments are required for this one. And test arrangements, I will tell you. So next is this samples. So as I told you that in case yield is almost 100%, so almost all the circuits are operating fine. So you require as less as say around say 1 or 2 random samples you can test and find. But in case of circuits, all these gates has to be tested. So because the number of what you call the number of faults can be very high, as high as 50% of the circuits may have fault. So all samples has to be tested. So that is why every unit has to be tested in case of circuits, while in case of classical systems like iron or heater or something, so as the number of faults are very less, so you can even take 3 or 4 random samples and you can do it. So now we will slowly see in the circuit basically about these 2 parts. These are not very, I mean we cannot explain at this initial lecture. That is, in case of circuits we generally do not go for repair, and in case of classical systems, if we find some repair, we can if we find out some of the electrical iron or some system have a fault, then we generally go for repairing and then we sell it in the picture. But in this kind of in VLSI circuits, test arrangements, basically it is not required. We have something, we test it, and then if we find out that there is some problems in case of the VLSI testing circuits is not performing finally, we generally then throw them out. That is, we do not believe in what you call repairing and all those things. So this is basic some difference in the VLSI testing as compared to classical testing. But some of the things like test arrangements in the design, okay, and test we do not have such type of stuff in case of classical systems. We will slowly see these points like binning and defective, non-repairing. So these parts we will slowly see when we will go into the other parts of your, slowly we will progress through the course, so we will see. So basic difference in case of normal testing, classical testing as well as the system VLSI testing is that classical testing almost all the products are correct. So random testing we do and very simple kind of test, so even a technician can do. But in case of VLSI, around say 40 to 50% or even more than that circuit can have defect. So you have to have all the circuit tested, and the test procedure is quite expensive. So you have to have really sophisticated instruments and engineers to do that. So that is the very basic difference between normal classical testing as well as system testing. So compared to classical systems, in VLSI testing occupies a very important parameter. So therefore in our course we have kept 1/3 module only for testing. So let us slowly go into the course, basic introduction. So in case of circuit, so what we will have? We have a manufactured circuit, we give the inputs. Now these inputs, as I told you, should be as less in number as possible. Then there is a golden response, that is we know that for this input this should be output. Then there is a comparator, so it compares this output with the golden response, and if all the responses match, we say that the circuit is operating fine. And also we also measure the delay in this case of requirement. So if this is the process, then we say the circuit is correct. Otherwise, if there is some mismatch between this and this, then we say that there is a fault and the circuit can be scrapped, or that is, it can be declared as a faulty circuit. So this is the basic digital test process. So this is an equipment. Now I have told you that I have to do testing of power, delay, so and so. So basically what does the test equipment look like? This is a automatic test equipment, we call it an ATE. So this is the test equipment. Here we put the circuit in a die in this case, and this big equipment as oscilloscope, CROs, pattern generator, logic analyzer, and they do most of the testing for you. So this is the automatic test equipment, and it is extremely expensive equipment, and very big companies can only afford this instrument. That we have to understand. So now before we go in more details, let us see what are the taxonomy of testing, that what are the different types of testing that is available in the market. So first question is when tested, that is the criteria, when do you want to test this circuit. So if you just do it before the manufacture, then it is called the manufacturing test. Also, after this circuit has been manufactured and it has been sold in the market, now it is in your laptop or in your palm top or your PDA, that also, at that time also you can have faults. So, before the circuit starts its operation, I can always have my circuit tested. That is like in your PC, whenever you start your PC, it shows that the RAM is being tested, and if all the RAM is fine, it gives an OK and then the circuit goes. So, therefore, many of the circuits are tested every time before the circuit starts. So, that is actually called built-in self-test. That is, circuit tests itself when the circuit is starting in operation. And for very mission critical systems like nuclear plant or airlines, flights or rockets, you can understand that the circuit should also be tested every time or concurrently when it is doing its operation. That circuit is operating, at the same time you have to say that you have to test itself. So, that is actually fault tolerance. That is, every time the circuit is, all the time circuit is operating, a person is monitoring it for its operation. So, these things are for mission critical applications like avionics, nuclear plants, etc. So, that is called online testing. The circuit is operating, as well at the same time you are testing the circuit. So, when the circuit is testing, these are the basic terminologies. Now, the question can be asked, who applies the test patterns, like we have seen for the NAND gate 0 0 0 1 1 0 and 1 1, and the question can be asked, who is applying these test patterns. So, if it is a manufacturing test, the ATE example I have shown you, so that is an ATE as the equipment. So, if the equipment applies the test pattern, we call it the ATE based testing. Like now in a BIST, so what is a BIST? BIST is built-in self-test. So, in this case what happens, the circuit is doing its operation, starting its operation. Before that we are applying some test patterns and we are getting a response. Now, if I have manufactured a circuit and I put it in your laptop, obviously you cannot bring the ATE machine and test your circuit. So, in that case, the test pattern generator and the test pattern and response analyzer are within your circuit. So, these are, we will slowly see towards the end of the course we will see how it is done. For equipment it is simple, you apply the patterns, you observe the response, but now the whole BIST of ATE circuit in miniature version, if you put in the circuit, then the test patterns can be applied from the circuit and also it can be analyzed in the circuit itself. So, if the patterns are applied within the chip, then it is in the case of a BIST. And now you see what is the case of online monitoring. In online monitoring what happens, the circuit is doing its normal operation, you are just monitoring. So, obviously in this case you cannot apply any pattern, the circuit is doing its operation, no patterns are applied, you are only monitoring and then you are judging whether the circuit is behaving properly or not. Now, third criteria is in which form it is tested. So, I think IC you have seen, we have all seen that this is a black chip with some pins here and there, this is called the IC. So, circuit has been fabricated and now you want to test it. So, this is actually called package level testing. The circuit has been packaged and you want to do the testing. I will tell you about our wafer. Now, you have also seen in a board, so you can have a PCB kind of a thing. So, I think all of you might have seen this is the printed circuit board and you have chips which are interconnected. So, this is called the board level testing. The circuit has already been in the board, now how can you test it? In case of IC, you can apply pattern in all the points, but in case of a board, you can only apply the pins, patterns which are the input output of the board. It is very difficult to control a pin here. Okay, in this circuit, because this pin is already connected to another part of a circuit, so directly getting an access to this may be difficult. But if it is in a IC level thing, you can easily access all the pins. So, if these chips are placed on a board and you are doing the testing, it is actually called the board level testing. Now, many number of PCBs are connected and you have made a system like a PC or a laptop, then now you have to do the testing. So, it is more difficult because in IC you can get access to all the pins of the IC. Now, if I put in a board, you can access only the pins which are in the input output of the PCB. All input outputs of the IC you cannot get it. Now, if I go for a system which is called the system level testing, testing somewhat becomes more difficult because now all the PCBs are connected in a system and you can have access to only the input output of the whole system. This is the system, there are many PCBs, in the PCBs there are many ICs, but you can only access the input output of the PCB, internally you cannot access. Now, there is something called wafer. Wafer is nothing but when the circuit is fabricated, it is a die and inside the die you will have a wafer. This is the direct circuit, which this circuit is actually put in the IC and then this is packaged. So, directly the wafer can also be tested because it is very easy to get access to all the pins. Like for example, if you have a IC like this, so there are lot of many gates, only few of them you can be accessed in the pin of the IC. But if you are accessing directly the die, so you can access many more pins of it. So, more system level you go, less is the number of pins you can access and more difficult is the testing. So, this is a very raw testing which is called non-packaged IC level test. You can have lot of pins. So, lower you go, the or more abstract level you go, the less number of pins you are having and so forth. So, but these are the different levels of testing in terms of when the circuit is tested. Now, the question is how is the test pattern applied. So, there can be two things, you can have static, you can plan ahead that what you want to apply, and also it can be adaptive level, depending on the output performance of the test you can change your test patterns. Then there is a few others like how fast is the test pattern applied. So, if you are doing at the normal speed of operation, that you are testing at gigahertz, so it is called at speed testing, but if your tester or ATU cannot supply speed test patterns at that level, you can do much slower, then it is called DC or DC slow testing. Now, again, who verifies the response of the output? That there should be some person who should match the golden response. So, if it is in case of an automatic test equipment, the equipment have everything, but in case of BIST, that is in case of a circuit or online tester, or in case of built-in self test, the on chip, there should be an on chip circuit, because in case of BIST, the chip is doing the online testing. So, the BIST is doing the BIST circuit is doing the testing. In case of online testing, the circuit on chip is doing the monitoring. So, in this case, the response analyzer sits within on the chip. So, in this case, if the person who matches the golden response is on chip, you can call it BIST online testing, and in case of ATE, it is ATE based testing. The equipment will do everything for you. Now, what do you gain and what do you pay? So, to pay, what do you have to do? You have to make test plan, you require test engineers, you require automatic test equipment, which I have shown you is extremely expensive equipment. So, more is a multi-dollar equipment. So, more time you spend on your tester, that many amount of money you have to give, that is more amount of test patterns or more tests you want to do, at more amount of time you have to use the ATN, more amount of test you have to pay. And if you are making a very intelligent test plan, then you have to pay the engineers, right. So, that is the test. Now, if you increase the test time, then you have to use more amount of ATE and more amount of money you have to pay. But if you make a very intelligent kind of a test plan, so that with less amount of equipment patterns you can test your circuit, then you should have a very good test plan. But again, then you have to pay, it has to be very sophisticated or very highly skilled manpower is required, which will again take the money. So, whole testing process is basically about trade off of economics. Like now, there is some people say that if your ATE equipment is very expensive, why not you put some extra circuitry on chip which can do a part of the testing for you. In that case, some of the patterns can be applied from the ATE and some of the patterns can be applied from the on chip circuitry. So, these things we will be seeing in details. So, that which we are again doing is a trade off between the ATE and your circuit. Like my ATE is a third party equipment, so I have to pay the ATE vendor. So, I have to, if I apply some amount of testing, I can do on chip circuitry like BIST, that is, or online testing kind of a stuff, or some circuit I put on chip to do the testing, then I can save some time or some amount of patterns in ATE. So, but again I have to increase my chip area. Then again there is a trade off that whether I should pay the ATE vendor or whether I put some extra circuitry on the chip for testing and I make the chip size higher. But now what do I get? I get a proper binning of chips. Testing in case of VLSI will never assure that all the chips are correct or I will repair my circuit so that I can sell all my circuit. That is a difference between VLSI testing and a classical system. Classical system, you test a circuit, then you say that all I repair, all my some irons I find faulty, I repair them and then I sell off to the market. But in case of VLSI circuit, it is not that. Some around from 100, say some 60% circuits are fine, which is good, and some 40% of circuits are bad, which I have to throw them off. Now, what I have my circuit VLSI testing is giving me, it is giving a very proper partitioning of 60 and 40. If I somehow sell a defective bad circuit into a good group and I sell it to a person, then that will be a big problem. So, that is how test economics will, what it will help me, test economics basically will give me a very proper kind of a it will give me inside the scene that in case of it is VLSI testing not proper concern that how many chips are being faulty. It is rather important that how many faulty chips are binned as normal. That if you have a faulty chip, you bin it and in a good and sell it to a person, the person will have a defective chip in his, that will be sold to him, that will bring bad reputation of the country. So, and because there is no scope of repairing a circuit. So, what you have to do? Our testing will give you a what you call good circuits as good and bad circuits as bad, so that you can go for a what do you call a proper VLSI testing, that is good is binned as good, fault is binned as fault, and then you give the proper thing to the circuit. So, in this course what we are now, this was the very introduction to digital circuit testing, the basic philosophy I have told you, and what is the difference between classical testing and VLSI testing I have told you, because till now in our mind we had an idea of classical system, but now I have explained you that VLSI testing philosophy is bit different from classical system. So, in this third module what we are going to read, so today we have seen about introduction, next in the few lectures we will be looking at structural versus functional testing and so forth, then we will go for fault simulation, then we will see combinational circuit test pattern generation, then we will go for sequential circuit test pattern generation, and finally we will see if I have to put all the testers on chip, that is built-in self-test, how it will go, and then we will also see something like built-in self-test and maybe some ideas on online monitoring. So, with this we come to the conclusion of the first lecture in case of VLSI testing, that was the introduction. In the next class we will see that how we can intelligently develop test patterns, or how we can intelligently plan test, so that I apply very less number of test patterns, yet get a very good confidence that my coverage is very good, that whatever binning I am doing is proper. Thank you.